Okay guys, so this video we're going to do pH effects on enzyme kinetics. And so let us do something first. Yeah, we have our standard Michaelis-Menten Michaelis-Menten or Michaelis-Menten. Oh man, I really got to learn to pronounce that. But yeah, whatever. Michaelis-Menten kinetics. These are your standard. If you've seen the last videos, you should already know. And this is the standard ones with only the forward reaction in this case. And there's an equilibrium between enzyme substrate and enzyme substrate complex. Now, what happens when a pH comes in? And in this case, we assume pH won't affect substrate. And why do we do that? Well, the thing is that if the pH is going to affect the substrate, you probably think that's a really strong acid. And if it destroys your substrate, it's either a strong acid or alkali. So, well, in that case, your enzyme would be totally destroyed by then. And usually the first thing to be affected by pH is the enzyme and not the substrate. So that is our assumption, right? Because the enzymes are much more complex, therefore they are easier to denature and break down and not work. So in this case, we are going to assume the pH doesn't affect the substrate. Okay, this is the assumption. And anyway, so if pH is going to affect the enzyme complex only, then we will have this case. Okay, so E plus H plus become EH plus. Okay. Anyway. Okay, so this is the protonation by Bronsted-Lowry acids. Then they will also have this equilibrium. So it releases the H plus E minus. Okay. So somehow there's a hydrogen in here that has attached itself to the enzyme, and in an alkaline condition it will shift to the right so that the Chatillier's principle is observed. Now of course this notation looks really weird because suddenly you have a H coming out from nowhere. So let's just put it this way. You have EH being your enzyme. Okay? So we have EH being your enzyme. So that it can get protonated, it can release a proton. So let's represent our enzyme by this. EHS, and this is EH. EH is your run-of-the-mill enzyme. So let's write it properly. EH plus S, forward and backward, and there you will go into EHS, and you go into EH plus P. So in this case, the notation is that the enzyme is denoted by EH. So the total concentration of enzyme is EH naught. So this is the total enzyme concentration. Okay, so let's do some a little more equilibriums. Okay, so you have E minus plus H plus, and then you have the protonation where you will have EH2 plus. So I'll just write that in. There'll be a H plus going into this. Therefore you'll get this. And of course the other thing I forgot to mention, the pH effects does not affect the enzyme substrate complex. Now of course in actuality it might, but this is a simplifying assumption. If not, it's going to get really complex. Yeah, it's going to get really complex. And then you will have the case of maybe something like a non-competitive or uncompetitive inhibition. So we are not going to discuss that at all. So that, yeah, your pH can cause non-competitive or uncompetitive inhibition, but for now we will not discuss that. Let's discuss the so-called you'll consider the pH like a competitive inhibitor. It's very similar in its equation form. So in the competitive inhibition, you have E plus I plus E becomes EI. So sometimes that I can become that hydrogen. So it looks like competitive, right? In this sense. Okay, so let's carry on. So you'll have a few equations as you want to do. The usual mass balance equations. So you have K2 into EHS. Okay, and this forward reaction, we'll call it the K base, and then this forward reaction we'll call the K acid. Okay, now I'll write it here. So you have KB going forward, because this is where the basic one's happening. Oh wait, rather no, I should just call it Ka, because this is acting as an acid, and this is where it acts as a base. Okay, so let me clarify again. Yeah, you have two reactions, one where your enzyme acts as a base, so forward is the base, backward is the minus base. You have a case where in an alkali where enzyme starts acting as an acid, so I just put Ka in front, where you'll have this hydrogen ion released, and K minus A. So this is K minus A. Okay, so just ignore this here. So anyway, we'll have our equations, then probably write them a little better later. But get the idea of what's going on first. So you have K2 into EHS, and you want to find out how this EHS changes with respect to time. And then, okay, this is number 1. Or this is number 1, I'll have it here. And this is number 2. So you have a DEHS dt equals to, it will equal to K1, this is K1, EH plus S forward, K1, EH, and S forward, and you have a minus K minus 1, EHS backward. So that's the backward reaction here, and minus K2, EHS, and that will be the product rate. Now of course you have the enzyme balance. Then you will have the standard free enzymes plus the basic form of the enzyme plus the acidic form. Okay, the acidic form and the basic form, and of course the enzyme substrate form. So you have 4 forms of the same enzyme. Right, so again we can assume rapid equilibrium. So that means the K2 is controlling, so we can just assume these two equal each other and we just cancel them off. So the second equation doesn't really become useful. So what we want is this EHS, and for this EHS we have to make this the subject. So next one, EHS equals excuse me, EH naught minus EH2 plus minus E minus EH, which is the standard free enzyme. Okay, so we need each of these. This one we'll probably know. We'll have to get these three. You'll have to get these three to get what we want. Okay, so we'll have to sort out the acid and alkaline ones first. So this is the acidic form, and this will be in equilibrium with this, correct? So the forward ones are, I just call it the Kb because this is acting as a base. This one's the K minus B. So in equilibrium lingo, okay, let's write this H plus and the EH into Kb equals the EH2 plus K minus B. Okay, so I'm going to bring this over. I'm going to write a big Kb. I'll write the H plus and the EH here. And you have this EH2 plus equals the H plus and the EH over big Kb. Okay, so we can substitute this back into our first equation. Let's go EHS equals EH naught minus H plus EH over big Kb. So now this is where it's acting as a base, I believe. So this is in acidic conditions, and then you have a minus E minus EH. So you can kind of guess, after a while you have to group up all these EH together. Okay, so let's do a similar thing for the basic form. Rather where the enzyme actually acts as an acid, which happens in an alkaline environment. So let's do this. Okay, I keep forgetting these brackets. So enzyme is acting as an acid during alkaline environment. Okay, and so what happens? We will have this. It will become a Ka forward, K minus A backward. So Ka into EH forward equals the K minus A E minus H plus backward. And of course this is a rapid equilibrium assumption again. So we'll have to make E minus the subject. So again we'll do our usual business. I'll bring the K minus A and the Ka together as a big Ka. So the minus is on top, the positive sides at the bottom. I'll write the remaining terms down. Then we'll want to make E minus the subject equals E minus equals the EH over Ka and H plus. There you go. So you have the EH naught minus. Okay, so I'm just going to factor. Never mind. Let's not factorize it. There's a careless mistake. We want to prevent careless mistake. So You have the E minus, which is the EH. You have the E minus, concentration of E minus, and EH over Ka H plus. So we have EH over Ka, and you have H plus here, minus EH. Okay, not too bad. You have EHS on the left hand side. So your final equilibrium is where you have EH. I'm just going to write the equation straightforward. So this is the final equilibrium equation where you have the EH and S forming EHS, or being in equilibrium with EHS. So again, I'm going to have a big K1 on the right hand side, EH and into S. Then we want to bring EH to be, we want to make EH the subject. K1 EHS over S. Okay, so we have more or less what we need. So let's factorize EH out, and then we'll substitute what we already know in. So I'm going to put H plus over KB. We just got to remember what KB is. So KB is when the enzyme is acting as a base. So this acid condition. And then we will have 1 over Ka H plus. Okay, so this brings to the bottom. This brings to the bottom here. This goes to the bottom here, sorry. This goes to the bottom. So yeah, that's what you get according to our definitions, and you have just 1. So there's a positive for this because this is already a minus. Then what we want to do is to bring EH to the left hand side. Okay, let's use another piece of paper. Yeah, another piece of paper. So I'm going to write all this down on the second piece of paper. Hopefully the video doesn't take too long. I'm really trying to hurry this up. EHS equals to EH naught minus EH H plus over KB plus 1 over Ka H plus 1. Bringing things to the left hand side. Okay, so I'm going to collect the terms at the bottom really quickly. I have the EH naught on the right hand side. I'm going to convert this into what we have previously derived earlier, which is this. So this EH equals to K1 EHS over S. So I'm going to put a plus here, and then pretty soon we can make EHS our subject. So again, what I've just done is to replace EH with what we previously derived from our equilibrium. I'm just going to do it on a new piece of paper. We have EHS plus K1 EHS over S. And you have the usual H plus KB. So 1 over KA H plus. Well, depending on how you define your KB and KA, your form of equation should be different. I mean, sometimes you have other K's on top, but it depends how you define your equilibrium constants. Otherwise, they should mean exactly the same thing. So, okay, EH not on the right hand side. So again, let's try and factorize it properly. Okay, so what we want to do is that we have this this bracketed thing. I'm going to lump this K1 and S and all this into a term called alpha. So alpha equals the K1 over S. So we don't, just grouping it up so I don't make the same careless mistake. You don't actually have to do this, but for the sake of reducing careless mistakes, you can absolutely and you should do this. So okay, let's go EHS 1 plus alpha equals EH naught. So that makes it a lot simpler to manipulate, so you don't have to write it so many times. And that's it. Very simple. Okay, Vmax over 1 plus alpha. Now let's substitute alpha back in and see what happens. So Vmax 1 plus. So this is a theoretical Vmax again. So K1 over S so H plus over KB over 1 over KA into H plus. So all this plus 1. So I'm going to multiply S to the top and bottom. Then you have this pH term here. And there you go. If you don't remember what pH is, it's just minus log of H plus. And you can substitute that in and out. That should be fine. Well, now you've kind of known how the pH actually affects the equation. It does not affect this Vmax per se, but it will affect this Km apparent, because if you make it look like the Michaelis-Menten equation, and Michaelis-Menten, you have the Km apparent here, which is this whole lot, and your pH will affect here. And that's based on the ionization of the enzyme only. Of course, if the enzyme substrate complex is affected, this equation will look a lot more complicated. It will look like something like the non-competitive case. Now it's looking something like the competitive case. And of course, you have the uncompetitive case as well, which I suppose is also possible, and then your form of equation will be different. So it depends on what your hydrogen ions or it depends what things are going to be, what form of the enzymes are going to be ionized. Then you have different forms of the equations, but the basic principles are the same. So thanks for watching, guys. I'll see you guys next time. Bye bye.